Hi, my name is Philip Friesen. It is May 1st, 2021. I am here to discuss my answers to the case connection for Unit 2. First, we will start off with case number 2, and this is the case that a 16-year-old female has recently been diagnosed with glycogen phosphorylase deficiency. Her first question is regarding how does glycogen work during exercise. During rest, our body primarily utilizes free fatty acid oxidation for energy because of its sustainability. However, the process is slow and is unable to be maintained. During bouts of exercise, our body shifts its focus to use glucose and glycogen because of its quicker use to produce ATP and accommodate the increased energy demands with exercise. Our muscles have glucose, which is ready to be utilized immediately in the plasma, and glycogen, which is the storage form of glucose, which is used for prolonged bouts of exercise. When exercise is sustained, glycogen will begin to be broken down to create ATP. During exercise or at rest, most substrates are being used in some percentage. However, the majority of the time it is at rest, it is free fatty acids that is being used. Her next question was regarding if she would still be able to take long walks. You would still be able to take walks up to a point. It is still a type of exercise, however, it is a lower intense type of exercise, so the body may be able to, again, utilize a slower process of beta oxidation and using free fatty acids for its energy source rather than glucose and glycogen. Also to note, there has been mention in the past of people experiencing what's called a second wind phenomenon. That is when, after exercising or walking for long periods of time, they begin to become symptomatic and they take a rest. After this rest, the body may be able to shift again its use to free fatty acids instead of glycogen, and the rest allows the body time to more or less catch up, and then you may be able to continue with exercise or your walks. So yes, you'd be able to walk for definitely for a given period of time, but it depends. Their third question is regarding if they were going to have to wake up at night to maintain blood glucose levels and feed. This would not be the case because, again, you're at rest, and during rest, most of the energy is being utilized through free fatty acid mobilization, as well as the use of liver glycogen. While like muscle glycogen, it needs to be broken down, liver glycogen is broken down by a different enzyme, different glycogen phosphorylase, other than the one that is used in muscle. So you'd still be able to mobilize and utilize the glycogen in your liver to maintain steady blood glucose during the fasted period at night. Their fourth and final question is regard to the buildup of lactate during high-intense exercise. With the type of disease that you do have, it may be hard to sustain any type of high-intense exercise, but this wouldn't be because of lactate buildup. The reason being is that lactate builds up or is produced at the end of glycolysis, and your muscle's ability to now utilize glucose, or more importantly, glycogen to glucose for energy production is limited. So the amount of lactate that your body would be producing or your muscles would be producing from the plasma glucose would be somewhat minimal. It's actually the contrary. You see less lactate buildup compared to normal populations. On to case number 4. In this case, there is a 2-month-old little girl who has begun to become jittery about 2 hours after feeding, and they did not notice this until after she started to sleep for more than 2 hours, and she was doing just fine with breastfeeding before then. I believe the child is suffering from glycogen storage disease. Glycogen storage disease is when they have a deficiency in glucose 6-phosphatase, which is required to dephosphorylate glucose 6-phosphate and allow glucose to then be transferred into the blood to maintain blood glucose levels. Her symptoms seem to meet all the criteria. She had been doing fine breastfeeding until she started to sleep for longer than 2 hours. At this point, the body is in a fasted state and will start to utilize liver glycogen in order to maintain blood glucose levels. And to do this, again, you would need to use glucose 6-phosphatase. This disease would also explain why epinephrine did not have any effects on increasing blood glucose levels. Epinephrine binds to the alpha-adrenergic receptor on the membrane of hepatic cells, triggering a cascade ending with the phosphorylation of glycogen phosphate. When glycogen phosphate is phosphorylated, the enzyme becomes active in the process of glycogenolysis, and the process of glycogenolysis occurs. Glycogenolysis is the breakdown of glycogen within the cells, and then utilize the glucose from the glycogen storage to maintain blood glucose levels. But because they are lacking the glucose 6-phosphatase, they are unable to perform the last step of glycogenolysis in order to allow free glucose out into the bloodstream. Some of the other options were hereditary fructose intolerance. This isn't likely the cause because the child never had any adverse effects from breastfeeding. And as we know, breast milk does contain fructose. It also doesn't explain why epinephrine did not have any effects on blood glucose levels. Similarly, galactosemia also is an issue with processing galactose, which is a sugar also found in breast milk. The patient had been doing fine with breastfeeding. It was only within the fasted state that they had issues. Again, just like with hereditary fructose intolerance, this would not explain how epinephrine did not have any effect on blood glucose levels when it was administered exogenously. Lastly, one of the options was glucose 6-phosphatase phosphate dehydrogenase deficiency. This is when you have a deficiency in the enzyme glucose 6-phosphate dehydrogenase, which is an enzyme that participates in the pentose phosphate pathway. And its primary job is maintaining NADPH in cells, mainly in red blood cells. NADPH then helps maintain glutathione levels, which help protect cells against oxidative stress. There's no indication of jaundice, dark urine, pale skin color, fatigue, shortness of breath, or rapid heart rate, which are symptoms of hemolytic anemia. Hemolytic anemia occurs because the downstream effects of early hemolysis of red blood cells when they are deficient in the glucose 6-phosphate dehydrogenase. And when this happens, red blood cells are unable to maintain the proper internal environment to function. The early cell death, because of the inability to maintain a proper functional internal environment, causes the cells to die, and the body is unable to maintain a high enough level of red blood cells because of the increased speed of turnover. That's it. Thanks for listening.